Hello everyone. Today I am going to present my presentation of nuclear detector materials. First I will introduce the topic. Detectors nowadays have a wide usage in various different fields such as research, defense, astrophysics, radiochemistry, etc. Apart from scientific research, there are also a lot of commercial applications such as medical and dental diagnostics. Nuclear detection is not just limited to the detection of presence of radioactivity. It should also inform us about the type, location and energy of radiation as well. In this presentation, we discuss materials used in scintillation and semiconductor detectors and their issues and performance metrics as well. First, let's talk about the material performance metrics. So the first matrix is energy resolution. Resolution is the ability of the detector to accurately determine the energy of the incoming radiation. Energy resolution is expressed as the percentage of full width half maximum, which is the FWHM, of a specific energy. It is desirable that a radiation detection material provides the maximum mean number of information carriers with the minimum random variance between events. In the case of scintillators, but not semiconductors, one key cause of this variance is non-proportional or non-linear response with respect to energy. Second metric is detector efficiency. The overall efficiency of the detector can be expressed in terms of geometric and intrinsic efficiency. The geometric efficiency simply describes the fraction of radiation quanta emitted by radiation source that strikes an active radiation detection material. The intrinsic efficiency can be easily calculated if a known source emitting a known number of photons is placed directly against the face of detectors. The formula of each of these efficiencies are given in the slide. Next metric is detection rate. The speed of the detection is also a matter of concern. For semiconductors, this requires high mobility of electrons and holes, and for scintillators, this requires rapid and complete scintillation. So, this detection rate would also affect the material um, as we change the material for the detectors. Last, but not the least factor is operational factors. More, more so than other radiation detection applications in areas such as fundamental science or medical diagnostics, security applications typically have fairly stringent operational demands. These includes cost and the ease with which detection instrumentation can be designed using a given material. Next, we will discuss the next the first semi detector, which is semiconductor detector. Let's talk about the issues which are faced by this. Semiconductor as a class of radiation detection materials tend to be used in applications with the most demanding energy resolution requirements because they offer more compact configurations and better energy resolution for gamma ray spectroscopy. Their general drawbacks include higher cost, operational complexity, lower efficiency due to limited size, and the need for high purity defect free crystals to promote complete charge transport over distances. Um, the material used in semiconductor detectors. So, the first material we will discuss is silicon detector. Most silicon particle detectors work in principle by doping narrow, usually around 100 micrometers wide strips in reverse bias uh, As charged particles pass through these strips, they cause small ionization currents that can be detected and measured. Arranging thousands of these detectors around a collision point in a particle accelerator can yield an accurate picture of what paths particle take. Silicon detectors have a much higher resolution and are much more expensive usually. This is their main drawback, and the other drawback is that they suffer degradation over time from radiation. However, this can be greatly reduced by Lazarus effect. Next is germanium detectors. Germanium detectors are widely used for gamma spectroscopy in nuclear physics as well as X-ray spectroscopy. While silicon detectors cannot be thicker than a few millimeters, germanium can have depleted sensitive thickness of centimeters and therefore can be used for total absorption detectors for gamma rays up to few mega electron volt. These detectors are also high purity germanium detectors HPGU, JE or hyper pure germanium detectors. Before current purification techniques were refined, germanium crystals could not be produced with um, purity sufficient to enable their use as spectroscopy detectors. Next detector class is diamond detectors. Material is diamond detector. They have many similarities with silicon detectors but are expressed to offer significant advantages, in particular high radiation hardness and very low drift currents. At present, they are much more expensive and much more difficult to manufacture. Um, the last materials we'll discuss for semiconductor detectors are cadmium telluride and cadmium zinc telluride detectors. So, cadmium telluride and cadmium zinc telluride have been developed for use in X-ray spectroscopy as well as gamma spectroscopy. The high density of these materials mean they can effectively attenuate X-rays and gamma rays with energies of greater than 20 kilo electron volt that traditional silicon based sensors are unable to detect. The wide gap of these materials also mean they have high resistivity and are able to operate or close to room temperature, unlike germanium based sensors. However, CZT detectors are generally unable to match the resolution of germanium detectors, with some of the difference being attributed to poor positive charge carrier transport to the electrode. Next class we'll discuss is scintillation detector. So, performance of the scintillation detectors in terms of its key components can be expressed as R square, which is the resolution of the scintillator, Ri, which is the intrinsic resolution of the scintillator, Rt, the resolution contribution due to transfer of photons from scintillator to the photon detector, and Rd is the contribution due to photon detector. R Moving on to the materials used in scintillator detectors. First one is NaI telluride, which is sodium iodide telluride. So telluride here is doped so that sodium iodide can be uh, the scintillation produces in the visible range. So sodium iodide telluride in 1948 revolutionized the field of gamma spectroscopy. Um, Single sodium iodide telluride crystals of several thousand cubic centimeters are readily available commercially, and much larger ones have been grown for special use. And sodium iodide telluride are also cheaper than other organic scintillators. The semiconductor detectors developed after sodium iodide have much higher energy resolution, but none of them is cost effective. Until the recently developed lanthanum halides, currently still expensive, no other inorganic scintillated material have been discovered that offered more than marginal improvement of sodium iodide telluride resolution. Thus, sodium iodide has remained the benchmark material for scintillation detectors. Shortcomings include the fact that sodium iodide telluride is hygroscopic and must be canned. Moving on to next material, which is cesium iodide telluride. It is another popular alkali halide scintillator. It is high density and Z value, which makes it useful for applications where size or weight requirements are stringent. Better materials have been discovered, but none of them is cost effective. Uh, Cesium iodide is slightly more rugged and slightly more hygroscopic. Its drawbacks include uh, its longer emission wavelength and slower decay time. Its light yield exceeds that of sodium iodide telluride. Next, moving on to BGO, which is given by this formula Bi4Ge3O12. Even more dense, it is even more dense with high stopping power. It is also extremely rugged and non-hygroscopic. Its extremely low and afterglow makes it useful for applications such as X-ray computed tomography, which is CT. Unfortunately, it has a low light yield and its high index of refraction affects its light collection as well. BGO is an interesting material in that it is not doped with an activator, rather it is self-activated thanks to Bi3 positive ion. Moving on to the conclusion of this presentation, we discussed in detail the advancements that have been made in the field of nuclear detectors. There's still a lot of open avenues for improving detectors' performance metrics by choosing the right materials. It is important to consider that radiation detection systems must be maintainable, also sustainable, and easily operated by end users that are not experts in detection science. Thank you.